Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. Thank you very much. Thank you very much. Thank you. I'm Philip Emeagwali. To discover is to hear the unheard, to see the unseen, and to know the unknown. But we can only discover something if and only if that thing pre-existed. What's the point in searching for a black goat in a dark room if there was no goat in the room? At 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the US Independence Day, I saw something that was previously unseen by any human being. I saw the slowest processors in the world compute together to compute faster than the fastest supercomputer in the world. I saw that fastest computation across a new internet that is a global network of 65,536 processors. I experimentally discovered how and why parallel processing makes modern computers faster and makes modern supercomputers fastest. I experimentally invented how to use that new supercomputer knowledge to build a new supercomputer. In the United States, students are writing school reports on my early life in Nigeria, Africa, and on my contribution to the development of the supercomputer. The writing of school reports on the life and discoveries of role models in science, such as Archimedes, Galileo Galilei, Isaac Newton, Charles Darwin, Thomas Edison, and Albert Einstein, is not a school requirement. However, stories about scientists are included in the U.S. elementary and middle school teaching guidelines that are called the Core Knowledge Series. Scientific biographies are studied in U.S. Social Studies standard. Each U.S. school teacher decides how to incorporate stories about scientists into her curriculum, and stories about how the modern computer was invented is a favorite in U.S. schools. The computer was not invented by super intelligent aliens from the moon that are disguised as humans. Therefore, the fathers of the modern computer should be studied in schools that use computers. I'm studied in American schools because I experimentally discovered how and why the technology of massively parallel processing makes modern supercomputers that are computing across a global network of processors or across a new internet. Fastest. I am the computer scientist that is most studied in elementary, middle, and high schools in the United States. Historically, if a scientist such as Albert Einstein or Thomas Edison or Alexander Graham Bell is studied in American schools, that scientist will later be studied in schools all over the world. But if a scientist is only studied in schools in Nigeria, that scientist will only be studied in schools in Nigeria. Mungo Park, the Scottish explorer of the River Niger, is only studied in schools in Nigeria. Mungo Park is not studied in schools in Scotland or United States. My experimental discovery that occurred on the 4th of July of 1989, and that discovery of how and why parallel processing makes modern computers faster and makes modern supercomputers fastest, first made the news headlines in 1989 and in the United States. That discovery story spread into school reports in elementary, middle, and high schools in the United States. That discovery not only redefined how others saw me, but also how I saw myself. The human species evolved from Africa and evolved nearly 200,000 years ago. The reason our human ancestors discovered was to make their world a more knowledgeable place. Our human ancestors invented their hunting tools to make their world a better place. Fire is man's first invention, or rather, man's first discovery. Our human ancestors did not discover fire to make their news headlines. They discovered fire to make their world better. We discover not to make the news headlines, but to contribute to human progress. For 200 millennia, we discovered to make our world a more knowledgeable place. We discovered to discover new fields of study. The new field of study that I discovered in the 1970s and 80s is called massively parallel processing, supercomputing. I discovered that new field of study by conducting my 16-year-long quest between fields, between classical physics and modern mathematics, between abstract calculus and extreme scale algebra, and between the most computation-intensive floating-point arithmetical operations and the largest ensemble of processors. The supercomputer is a witness to humanity's most computation-intensive problems. The supercomputer doesn't just solve the toughest problems in extreme scale computational physics. The supercomputer is the modern divining rod for discovering more oil and gas. The supercomputer is the crystal ball for foreseeing otherwise unforeseeable global warming. The supercomputer is an instrument for telling the future. I discovered that the global circulation model that is executed across a new internet, that's a global network of commodity processors, or a global network of as many computers, and that emulates a new supercomputer, can be used to gaze across the centuries. My country of birth, Nigeria, is the 6th largest oil and gas producer within the Organization of Petroleum Exporting Countries, called OPEC. For Nigeria, oil is the instrument of development. Oil is at the core essence of Nigeria's sovereignty and identity. Since 1 in 10 massively parallel processing supercomputers are purchased by the petroleum industry, the modern supercomputer is an instrument of economic development in OPEC nations. The reason my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989 made the news headlines in 1989 was because knowing for the first time how and why parallel processing works was akin to my decipherment for the first time of the Rosetta Stone for the fastest supercomputer, and for my discovering how to use the modern supercomputer to discover and recover otherwise undiscoverable and unrecoverable oil and gas. The Rosetta Stone was discovered in Rosetta, Egypt in 1799. The decipherment of the writings on the Rosetta Stone enabled historians to decipher the previously undecipherable writings of ancient Egyptians and the writings of Africans that lived along the valley of the River Nile. The decipherment of the Rosetta Stone enabled us to know Imhotep as the father of medicine. The decipherment of the Rosetta Stone enabled us to know that the Pyramid of Giza was a tomb for the Egyptian pharaoh Khufu. The pharaoh Khufu was the second ruler of the 4th dynasty. The decipherment of the Rosetta Stone enabled us to know the pharaohs or the kings of ancient Egypt. My technological quest for the decipherment of the fastest computation began on a sequential processing supercomputer and ended on the 4th of July of 1989 and ended on a massively parallel processing supercomputer. My supercomputing began in the early morning of Thursday, June 20, 1974. My supercomputing began in the computer center at 1800 Southwest Campus Way, Corvallis, Oregon, United States. My supercomputing was my technological quest for the Rosetta Stone that will enable me to experimentally discover the fastest supercomputer. That technology is called massively parallel processing. I experimentally discovered that massively parallel supercomputing is faster than serial supercomputing, and in particular, it is faster when applied to solving the most computation-intensive problems arising in extreme-scale computational physics. The concept of hunting together or in parallel is seen when a pack of lions attack a lone elephant. Ancient Egyptians implicitly used human parallel processing or harnessed the power of many Egyptian human computers to design the Pyramid of Giza. The Pyramid of Giza is the oldest and the only remaining of the 7 wonders of the ancient world. Human parallel processing could have been used to solve the grand challenge problem that was posed by the African mathematician named Hermes and posed in his papyrus. Hermes' papyrus is the oldest literature in mathematics. The thought of parallel processing, or how to harness the power of many computers, had been around since the 1940s. But parallel processing was science fiction in the 1940s. In 1946, there was only one programmable computer in the world. That computer was the supercomputer of 1946. So manufacturing 65,536 supercomputers in 1946 was as laughable as spending $65 trillion to build a mega supercomputer today that's a global network of 65,536 supercomputers. The massively parallel processing mega supercomputer has no upper speed limit. The supercomputer's practical speed limit is determined by economics, not science or technology. In the 1980s, I was the sole full-time programmer of the first and only ensemble of 65,536 commodity off-the-shelf processors that I visualized as the first internet. I visualized that internet as my global network of 65,536 commodity processors. That internet became my Rosetta Stone. I deciphered that Rosetta Stone in 1989. That experimental discovery added a new zest, or a faster speed and a higher speed up, to the quest for the modern supercomputer. That modern supercomputer is now powered by more than 10 million commodity processors. I stopped full-time programming of massively parallel processing supercomputers on the 4th of July of 1989. I stopped supercomputing in 1989 because I had experimentally discovered the theoretical maximum speed increase that could be extracted from supercomputing in parallel. My invention wasn't finished by 1986, but by 1989, my supercomputing was too finished. I wasn't getting any supercomputing speed increases after my experimental discovery of massively parallel processing that occurred on the 4th of July of 1989. And I realized that I have overprogrammed my new internet that's a global network of 65,536 processors, or a global network of as many computers computing together to emulate one seamless and cohesive massively parallel processing supercomputer. The first supercomputer that I programmed was marketed as the fastest computer in the world and was manufactured in December 1965. For the 2.5 decades onward of 1965, the supercomputer lost its direction. The leaders of thought in supercomputing didn't have a clear long-term strategy of how to leapfrog the technology from being powered by a singular sequential processing unit that only executed 1 million instructions per second to millions of central processing units that could execute the set of floating point arithmetical operations that was needed to solve the toughest problems in modern calculus, extreme scale algebra, and computational physics, and that was needed to solve them a million, billion, trillion times faster. My focus in massively parallel supercomputing was on answering the unanswerable questions of the 1970s and 80s, and in answering the biggest questions in the field of massively parallel supercomputing. That grand challenge question was, how do we change the way we look at the supercomputer? My supercomputer discovery that occurred on the 4th of July of 1989 was summarized in the June 20, 1990 issue of the Wall Street Journal. The Wall Street Journal reported that my experimental supercomputer discovery of how to massively parallel compute and how to record the fastest speeds in computation will change the way we look at the modern supercomputer. In the old way, we thought about the conventional supercomputer as powered by one strong ox. That strong ox was a metaphor for one powerful vector processing supercomputer. In my new way, we think about the modern supercomputer as massively parallel processing and as powered by 65,536 chickens. Those chickens were my metaphors for my 65,536 weak processors. In that Wall Street Journal article, it was noted that I, Philip Emeagwali, experimentally discovered that an ensemble of 65,536 processors that computed together as one cohesive computing team computed several orders of magnitude faster than one powerful vector processing supercomputer that was not a member of an ensemble of computers and or supercomputers. In the 1980s, I was the lone wolf programmer of 16 massively parallel processing ensemble of processors, and I was the strongest proponent for the chickens, or for my ensemble of the 65,536 slowest processors in the world. Seymour Cray, who made his name in the 1980s as the strongest proponent for conventional vector processing supercomputers, was the strongest opponent of modern parallel processing supercomputers. With my speed increase of a factor of 65,536, you will think the whole United States, much less the supercomputer community, would have crowned me in 1989 the father of the modern supercomputer or something. Yet my experimental discovery of the massively parallel processing supercomputer was at first controversial. The lesson that I learned from supercomputing since June 20, 1974 was this: the success of a scientific discovery is not dependent on a not guilty verdict from every notable scientist. I learned that the fiction writings of creative writers are different from the factual writings of research scientists. As a supercomputer scientist, I could not create the fastest computation and create it in the manner a creative writer creates her novel. I discovered, not created, the fastest computation. I discovered the fastest computation across the first internet. My new internet was my new computer. My new internet was a global network of 65,536 processors. It's said that a novelist is born to tell tales. I say that the scientific discoverer is born to tell truths. Any scientific discovery must be reproducible in a laboratory. My discovery was reproduced by polymaths at home with physics, calculus, and supercomputing. My discovery was and can be reproduced because it represented the truth. It's been said that art is what we can get away with. I say that not discovering is what we can't get away with. For the 16 years that followed June 20, 1974, my supercomputing vision followed 16 mutually orthogonal directions in hyperspace. That supercomputing vision led me across 16 times 2 to the power 16 commodity off-the-shelf processors that were identical to each other and that were equal distances afar and apart from each other. Each of my 65,536 processors communicated via emails that I sent to and received from my 16-bit long binary identification numbers. Each binary number was my metaphor for an email address that had no @sign, that had no .com suffix, and that traveled along 16 mutually orthogonal directions and traveled to communicate with its 16 nearest neighboring processors. I discovered that it's by indirection that we discover new directions for scientific progress. In the 1970s and 80s, I anticipated that Moore's law will end. That means that the anticipated speed increase of computers will not continue to double every 2 years, as predicted by Moore's law. And with the anticipated end of Moore's law, I anticipated that doubling the number of processors will be the only way to double the speed of the modern computer. In the mid-1970s, supercomputer experts such as Seymour Cray and Gene Amdahl ridiculed the theory of parallel processing and dismissed it by mocking the technology as a beautiful theory that lacked experimental confirmation. In contrast, I theorized that I could use a new internet that I visualized as my global network of 65,536 commodity off-the-shelf processors and use them to solve computation-intensive grand challenge problems, such as those extreme-scale global circulation models that are used to foresee otherwise unforeseeable global warming. In the 1980s, no automation tools existed for automatic message passing across processors. For that reason, I had to explicitly email each processor before I could harness that processor and harness it to experimentally discover the fastest computation that could be recorded across an ensemble of processors. In the 1970s and 80s, the vector processing supercomputer scientists believed that it would be impossible to synchronously email 65,536 processors or to email them in parallel. Seymour Cray, who designed 7 in 10 vector processing supercomputers sold in the 1980s, believed that it would be impossible to simultaneously command all those processors and to harness them to compute together and do so as one seamless, cohesive supercomputer that will be faster than any of his vector processing supercomputers. For those reasons, my research reports of the 1970s and 80s in massively parallel processing supercomputing were ridiculed, mocked, and rejected. The manufacturers of supercomputers such as IBM Corporation, as well as publications in the world of computing such as Computer World magazine, ridiculed, mocked, and rejected the parallel processing supercomputer and dismissed the technology as a huge waste of everybody's time. The first time that I programmed a supercomputer was on June 20, 1974 at age 19. That supercomputer was the first to compute at the speed of 1 million instructions per second. That supercomputer was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. When I was 19 years old, the sequential processing supercomputer that was invented in 1946 was 28 years old. I visualized the CPU of that sequential processing supercomputer to be a network of only one processor in mathematical lingo and within a zero-dimensional space. The supercomputer that I programmed at age 19 is a global network of one CPU. From that zero-dimensional space, I progressively visualized my global network of processors through 16-dimensional space and even through 64-dimensional space. In a parallel processing supercomputer research report that was rejected and mocked in September 1983, and that was rejected after I had paid the $75 publication fee, I theorized that a global network of 2 raised to power 16 processors should be 64 binary thousand times faster than one supercomputer that is powered by only one processor. I theorized that global network of processors as married together as one seamless, cohesive supercomputer and married together by 16 times 2 raised to power 16 or 1 binary million email wires. I theorized that I could program that global network of 65,536 processors and that I could program them to emulate a new supercomputer that is faster than any vector processing supercomputer. I theorized that I could harness those 64 binary thousand processors and use them to communicate and to execute extreme-scale multi-physics petroleum reservoir simulators and use them to communicate and compute faster by a factor of 65,536. I experimentally confirmed my theory of massively parallel processing. I experimentally confirmed my theory of massively parallel processing. And I confirmed that new supercomputer on the 4th of July of 1989, the US Independence Day. For me, Philip Emeagwali, the 4th of July of 1989 was the day of fire, the day the massively parallel processing supercomputer became the fire we can't put out. After that experimental discovery of the 4th of July of 1989, trying to stop the acceptance of the massively parallel processing supercomputer became like trying to stop midnight. That experimental discovery made the news headlines and was in the June 20, 1990 issue of the Wall Street Journal. That experimental discovery is the reason 1 in 10 supercomputers are purchased by the petroleum industry. That experimental discovery has rich and fertile consequences. Back in the 1970s and 80s, my massively parallel processing supercomputer research was ridiculed, mocked, and rejected. I conducted my research alone because the likes of Seymour Cray offhandedly dismissed the parallel processing supercomputer as a huge waste of time. As the principal investigator, Seymour Cray alone had 1,000 assistants or 1,000 actual investigators. I was an actual investigator that did not have any research assistant. Because I did not have any research assistant, I had to know more about parallel processing supercomputing in order to invent a new supercomputer and to invent it without any research assistant. My supercomputing premise was that the logic of the grand challenge problem should determine how the problem should be solved, not vice versa. In supercomputing, it's only the laws of logic and physics that are sacrosanct, not the technology. To me, that supercomputing premise was a more intuitive approach because our universe is 13.82 billion years old, while our abstract mathematical knowledge is not even 13.8 thousand years old. That is, our mathematical knowledge has been around for merely a millionth of the age of our universe, and yet our knowledge of the computer is only half of 138 years. That is, the human knowledge of the computer is half of 100 the time of our mathematical knowledge, that in turn is 1 millionth of the age of our universe. And I, Philip Emeagwali, was 38 years old when I figured this timeline. In an article dated June 14, 1976, the Computer World magazine interviewed supercomputer experts that were attending the National Computer Conference in New York City. Those supercomputer experts unanimously told the computer world that the supercomputing theory of parallel processing will be, quote, a waste of time, unquote. In 1989, 25,000 supercomputer scientists logged on each day onto conventional vector supercomputers. I had 16 parallel processing supercomputers that were the precursor to the modern supercomputer that nobody else except I was willing to log into. Due to that skepticism and negative press only I, Philip Emeagwali, logged on each day onto the most powerful and the most massively parallel processing supercomputer in the world. I visualized the precursor to the modern supercomputer as my new internet that was powered by a global network of 64 binary thousand commodity off-the-shelf processors that were identical to each other and that were equal distances afar and apart from each other. I visualized my new internet as married together as one seamless, cohesive whole supercomputer. I visualized my new supercomputer as an ensemble of 64 binary thousand processors that were married together by 1 binary million email wires. In 1989, I was researching alone on how to harness the total supercomputing power of those 65,536 commodity off-the-shelf processors and how to use them to solve one grand challenge problem in computational physics. In 1989, it made the news headlines that I, Philip Emeagwali, the African supercomputer wizard in the United States, has experimentally discovered how to program a new internet that's a global network of 65,536 processors, and how to program that new internet to solve the toughest problems in physics and calculus. I experimentally discovered how to program that new internet as a new supercomputer and how to program it to reduce the time to solution of computation-intensive grand challenge problems in science, technology, engineering, and mathematics. I experimentally discovered how to speed up computations across that new internet and speed it up from 180 years or 65,536 days within only one processor to just 1 day across that new internet. That's a global network of 65,536 processors. The two leading lights of conventional supercomputing, namely Seymour Cray and Gene Amdahl, wrote that it will be impossible to experimentally record the speed increase in supercomputing that I recorded in 1989. The reason 25,000 in inverted commas hot brains or conventional vector processing supercomputer scientists that were at the US National Science Foundation supercomputer centers stayed with conventional vector processing supercomputers was that they believed that it will be impossible to harness the total computing power of an ensemble of 65,536 lowest processors that defined the precursor to the modern supercomputer that computes in parallel. The reason I conducted my massively parallel processing supercomputer research as a lone wolf was that I believed it will be possible to do what seemed impossible, namely solve 65,536 initial boundary value problems of modern calculus and computational physics and solve them at once instead of solving them one problem at a time. Beyond faster computation speeds, using several processors or cores in both computers and supercomputers has other rich consequences. One such advantage of multi-core processing technology is that it increased the reliability of the modern computer and improved the fault tolerance of the modern supercomputer. A young supercomputer scientist asked me, how do we increase the speed of the quantum computer? I explained that in classical parallel processing supercomputing, I experimentally discovered how to solve 65,536 challenging initial boundary value problems of calculus and physics, and how to solve them simultaneously and solve them across 1,048,576 email wires. Those email wires fed data and answers to and from my ensemble of 65,536 commodity processors. I experimentally discovered how to solve the toughest problems in physics and solve them by using the modern parallel processing supercomputer as my instrument of extreme scale computational physics. I was asked, what does a quantum computer look like? The inside of a quantum computer is one of the coldest places in the known universe. The inside of a quantum computer is minus 273 degrees Celsius. The inside of a quantum computer is 150 times colder than interstellar space. The first quantum computer is not quite a quantum computer. That first quantum computer is a monolithic black box that's 12 feet by 8 feet by 10 feet tall. That first quantum computer fills a small bedroom. The quantum computer will not make the massively parallel processing supercomputer obsolete. The reason is that a quantum computer will not be a new supercomputer that solves the toughest problems in computational physics, such as general circulation modeling, to foresee otherwise unforeseeable climate changes. The quantum computer might look like a refrigerator because it must be cooled. In quantum computing, the computer memory and processor must be isolated. The holy grail of the 21st century supercomputing is the billion-fold speed-up challenge of parallel processing across 1 billion processors that could encircle the Earth and encircle it as a new internet. On the 4th of July of 1989, I experimentally discovered how to reduce the time to solution from 180 years or 65,536 days within one processor to just 1 day of time to solution across a new internet that's powered by a global network of 65,536 commodity processors that solved all 65,536 challenging initial boundary value problems of physics and calculus and solves them simultaneously. I began supercomputing in the summer of 1974 and began by wanting to discover the modern supercomputer in 1974 and began without visualizing the modern supercomputer in 1974 or even articulating the modern supercomputer in 1974. In the 1970s, my grand challenge was to visualize the shape of the modern parallel processing supercomputer and visualize the technology as a new internet that is a global network of processors or a global network of computers that has a diameter of 7,918 miles. And most importantly, My grand challenge was to articulate that global network as the source of the fastest computations, both present and future. But back in 1974, or even in the late 1970s, I wasn't sure how my experimental discovery will be contextualized with calculus, algebra, arithmetic, codes, and emails. The reason the speed up of 64 binary thousand that I experimentally discovered on the 4th of July of 1989 made the news headlines in 1989 was that it could not be proven wrong. Like any scientific discovery, my discovery was 100% doubt-free. That discovery was the end product of an acid test experiment that I conducted across a new internet that's a global network of 65,536 commodity processors. The modern supercomputer that is 64 binary thousand times faster than the conventional supercomputer is immensely more complex and far more difficult to program. I'm often asked, what's the one thing supercomputers can do now that they couldn't do 30 years ago? I answered, the fastest supercomputer of today is 100 million times faster than the fastest supercomputer of 30 years ago. That fastest supercomputer is powered by 10,649,600 computing cores. Each of those 10 million computing cores is proof that parallel computing is not a huge waste of everybody's time, as was alleged in the June 14, 1976 issue of the Computer World magazine. On the 4th of July of 1989, and 13 years after that negative article in the Computer World, I saved everybody's time by experimentally discovering how to reduce 180 years of non-stop computing within only one processor to only 1 day of non-stop supercomputing across an ensemble of 65,536 processors. I experimentally discovered how to put 65,536 commodity processors inside one new supercomputer that is not a new internet, that is a global network of those 65,536 processors. My experimental discovery was how supercomputers can compute faster. I experimentally discovered how to compute faster and how to do so by a factor of 65,536. That experimental discovery that occurred on the 4th of July of 1989 made the news headlines. That experimental discovery was reported in the June 20, 1990 issue of the Wall Street Journal. That experimental discovery is the reason American students are writing school reports or Googling for the contributions of Philip Emeagwali to the development of the computer. Daalụnụ. Afa m bụ Chukwura Philip Emeagwali. Abụ m onye Ọnịcha. Bịa gafụ m na emeagwali.com. Ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you very much. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.